Okay, so I want to review some ratio and root test problems to test for absolute convergence. So here it's a selection of these different problems. They vary in difficulty a little bit, but we're going to use either the ratio test or the root test on all of these. So let's see what happens when we do that. So starting with this first problem, we see a factorial, and we know that the only real way to get a factorial to cancel is to use the ratio test. So let's try that approach. The nth term is n factorial over 100 to the n. So the n plus 1 term is n plus 1 factorial over 100 to the n plus 1. Again, just replacing wherever we see n with n plus 1. So this means that we want to consider the limit as n goes to infinity of the absolute value of the n plus 1 over the nth term. And we're going to test and see if that is less than 1, which would imply that it converges absolutely. So we want to see what this expression turns out to, and then see if it's less than 1. Well, that means the limit that we're looking at, how much space do I have? Probably want to keep going this way, huh? We're going to do the limit as n goes to infinity of n plus 1 factorial over 100 to the n plus 1. And we're going to divide, but we're going to keep change flip. These things are already positive, so I don't need the absolute values. So this is going to be 100 to the n over n factorial. Again, right, we're dividing by an. Dividing by that fraction means we're multiplying by the reciprocal, so it looks like this. So notice now you have n plus 1 factorial on top, n factorial on bottom. And so we're going to cancel everything but n plus 1 with the factorials. Then what's left, we have 100 to the n plus 1 power in the denominator, and 100 to the n in the numerator. And so we have just 1 left over in the denominator. So we're looking at the limit as n goes to infinity of n plus 1 over 100, and that's going to blow up to infinity. And so the question, is this less than 1? No. So the conclusion, so the series diverges. Again, what happened? We found the nth term is n factorial over 100 to the n. The n plus 1 is the same thing, but replace n with n plus 1. So now when you do a to the n plus 1, or not 2 though, an plus 1 divided by a to the n, the expression will look like this. And now we want to simplify this and take the limit. Factorial means you multiply it by all the numbers before it. So n plus 1 times n minus 1. And then you're dividing by n times n minus 1 all the way down. So all the terms, right, it looks like this. Dot, 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 times 2 times 1. And so if you divide that by n times n minus 1 times n minus 2, dot, 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 all the way down, then the n's cancel, the n minus 1's cancel, the n minus 2's cancel, and everything in between there will cancel. So you're just left with n plus 1 in the numerator. Similarly, if you have 100 to the n and 100 to the n plus 1, you can always write that as 100 to the n over 100 times 100 to the n. Right, raising it to the n plus 1 power means you're going to do 100 to the n and then times an extra 100. So these pieces will cancel and you're left with 100 in that denominator. So all this stuff cancels. You're just left with this expression, limit as n goes to infinity of n plus 1 over 100. Now the numerator is going to blow up to infinity, the denominator is stuck at 100, so this whole thing is just going to blow up to infinity, and we ask, is this limit going to be less than 1? No. So this does not converge absolutely, and because these terms are already positive, it just has to diverge. Again, we saw the factorial there, so we knew we had to use this ratio test. Now, looking at this one, you may see this and realize that neither test really stands out immediately. My advice is to use the ratio test whenever you have a factorial, absolutely always, but whenever there is a nth power, the nth root test is a good way of solving those. So immediately, we don't really directly see either one, but we actually see an n plus 1 power here. So that gives us some guidance that maybe the root test can help us. So the root test wants us to look at the limit as n goes to infinity of the nth root of the an terms. So we notice, if we were to write that out here, limit as n goes to infinity of the nth root of, now when you take the absolute value of this piece, that negative 10 is going to turn into just positive 10 to whatever power, so the n plus 1 power, and then n to the 10th is just stuck as n to the 10th. Taking the absolute value doesn't do that. So can we find some way to handle this expression? Can we do the limit as n goes to infinity of, now remember, doing this nth root is the same as doing a fractional exponent. So the nth root is really the 1 over n power. And because we have a fraction, we kind of get to distribute the exponent to top and bottom. So this is n to the 10 over n divided by 10 to the n plus 1 divided by n. So let's see if we can handle the numerator and the denominator. Now the issue here is that our immediate conclusion might be, oh, if we're doing 10 over n, that limit as n goes to infinity should make this go to 0, but we're having n as the base there, so it's a little bit more complicated than that. We don't get to just immediately say what that goes to. In fact, really what I want to do is rewrite this as n to the 1 over n to the 10th. Right, move the 10 to the outside there. Now our limit as n goes to infinity is still stuck. And as for the denominator, what we're going to do is just divide both pieces by n. Right, n plus 1 divided by n. Just distribute that to both parts. N divided by n is 1. 1 divided by n is, well, 1 over n. And now something incredibly interesting happens with this limit. In fact, it turns out that 1 over n is heading to 0 really quickly, whereas n is heading to infinity at a pretty normal rate. And what happens is something is raised to the 0 power, that's going to go to 1, and so it does actually turn out that that limit is just 1. Kind of the way that you would hope if it was. Now, I am trying to tell you right now that that limit is 1, rather than like proving it to you. So this is really, kind of a weird limit to take, but take my word for it, it turns out that that limit is 1. Now, can we do this limit in that denominator, 10 to the 1 plus 1 over n, as n goes to infinity? Well, as n's going to infinity, 1 over n is heading to 0. So can we do that limit? Well, sure, that piece is just going to 0, so this just looks like 10 to the first, which is just 10. So it turns out the limit from our root test is 1 to the 10th, which is just 1, over 10 to the first, which is just 10. So this is the value of our limit, and we ask, is this less than 1? Is 1/10 less than 1? Yes. So the series converges even more than just saying converges normally, because we use the absolute values here, right? This is the root test. It tells us it converges absolutely by the root test. Again, this is pretty weird. Recognizing that n to the 1 over n goes to 1 is a little awkward. Right? Limit as n goes to infinity of n over 1 of the n is equal to 1. How can we see that? Well, again, the argument that I'm making is that the exponent goes to 0 a little bit quicker than n blowing up to infinity. And when I talk about like quicker, right, that's rate of change, that's speed, that's rate of change, that's derivative. And what's the derivative of 1 over x? X to the negative first. We'll drop the power down, subtract 1 from the power. That's just negative 1 over x squared. And what's the derivative of just the n piece? Well, that looks like just x, so the derivative of x is just 1. And so the question is, which one of these is changing faster, is increasing faster? Well, it's going to be this, right? So truly that exponent is blowing up, or decreasing, I should say, way more than what this one is increasing. So that's like the motivation for why this limit goes to 1, right? Trying to argue something about that. I'm not proving it, I'm just kind of saying this is how we can see the behavior behind these things. I'm not constructing any like proof right now for that. I'm just trying to argue in favor of why this turns out to be the case. Okay, so again, this is kind of awkward, but it's doable if, this is even doable. Right, the challenge with this problem is this piece, essentially. So can we do this problem using the other test? Would that help us avoid this kind of problem where we hit that limit that we don't know? Well, let's make some room and see what the ratio test would look like for this one. So what is the nth term? N over 10, negative 10 to the n plus 1. What is the n plus 1 term? N plus 1 to the 10th over negative 10 to the... Now plugging in n plus 1 there, n plus 1 plugged into n plus 1, right? That's going to look like n plus 2. And so we would want to find the limit as n goes to infinity of the absolute value of an plus 1 over an. And that's going to look like the limit as n goes to infinity. Taking the absolute value of those pieces just turns the negative 10 to positive 10. So that's going to be n plus 1 to the 10th over 10 to the n plus 2 divided by an. It's going to make us keep change flip. 10 to the n plus 1 over n to the 10th power. So the question is, can we make sense of what this limit is supposed to be? Well, certainly we can look at the tens and notice that 10 to the n plus 2 has one more 10 than 10 to the n plus 1. So we're left with 10 in the denominator over here, and we are left trying to figure out what can we say about n plus 1 to the 10th over n to the 10th. Well, hold on for a second. This exponent isn't some unknown, right? This is just 10. Can we do n plus 1 to the 10th power? Like, can we FOIL that out all the way? In theory, we can, but hold on, we're doing a limit as n goes to infinity. Do we really need every piece of this? Well, no, right? The behavior of these kind of things is really determined by the leading power. And so you can kind of recognize that n plus 1 to the 10th is going to lead with an n to the 10th. And notice that this 1/10 can come out front of our limit. Limit as n goes to infinity of n to the 10th plus some lower powers of n divided by an n to the 10th. Again, the leading term really determines all the behavior here. And so, do L'Hopital's rule, if that's how you want to say it, what's going to happen? Well, these pieces are going to cancel, and this is just going to look like 1. So this is just going to go to 1/10. And so the question is this less than 1? Still, yes. So this is a way to handle this problem using the ratio test, or instead of having to do some really arbitrary limit that we may not even recognize, we just do, and I say just in air quotes, n plus 1 to the 10th. And that's not as arbitrary, that's just complicated. But we recognize, well, because we're taking this limit as n goes to infinity, we really only care about the leading term, which just turns out to be n to the 10th. And so n to the 10th plus some lower degree stuff divided by n to the 10th, that limit as n goes to infinity is going to become 1. And so it's 1/10 times 1, which is just 1/10. And we ask the same question, is this less than 1? Yes. So this test would be the ratio test, and we would see that this also converges absolutely by the ratio test. So either one is valid, it's just what you're comfortable doing. Do you want to do this limit, or do you want to do this limit? Okay. Next. Okay, so this problem is actually fairly difficult. So this is a good bit beyond what I want, what I would ask y'all to do. I would just hope that we're able to follow along enough that we can see what happens with this one. So we are going to use the ratio test. Again, we have a factorial, and the only real method of canceling anything there is to do that. So let's write what the n term is. That's n factorial over n to the n. And the n plus 1 term, n plus 1 term is n plus 1 factorial over n plus 1 to the n plus 1 power. Now again, this is fairly deceptive because we would love to just take the nth root here and cancel that out, but talking about the nth root of n factorial is really weird. So for that reason, we're going to use the ratio test, because at least that cancels the factorial, and maybe something nice can happen in terms of handling the n plus 1 to the n plus 1 power. So that means we're going to do the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1, and then divide by n factorial over n to the n, which turns into multiplying by n to the n over n factorial. And again, the point of this is that the factorial pieces are going to cancel, so we're left with limit as n goes to infinity. We're left with the n plus 1 on top, but no more factorials, at least. But we are left with the incredibly awkward piece of having n plus 1 to the n plus 1 power, and then an n to the n in our numerator. Now, something interesting happens here. Notice that this n plus 1 is being divided by n plus 1 to some power. So again, recognize raising something to the power is saying it shows up that many times. You're multiplying all those pieces together. So you can cancel, right? I'm going to rewrite that denominator as n plus 1 times n plus 1 to the n. Right? Saying it's to the n plus 1 power means you multiply it by itself n many times, and then once more. But I'm emphasizing we can rewrite it like this because that will make this piece cancel with this piece, but we still have n to the n. Now what's nice is that now we have two pieces that are both to the nth power, so that lets us, again, what we're left with is n to the n over n plus 1 to the n. And now since those are both to the nth power, we can write it as a single fraction, all to the nth power. Now, there are a few different ways of looking at this, of handling this. So now that we have it written like this, we see an actual limit that in theory we might be able to take somehow. Now, if you're sitting at your computer or with a calculator that's really fancy, you can tell it, hey, take this limit, right? And it's going to turn out, this is really silly, do we remember n plus 1 over n to the n, which we can also write as 1 plus 1 over n to the n? You might remember that the limit as n goes to infinity, limit as n goes to infinity, of this thing is one of the weird definitions that we have for our natural number e. It turns out that n plus 1 over n raised to the nth power is just equal to e. Well, how does this compare to that? It's just the reciprocal, right? This is n plus 1 over n. This one that we're considering is n over n plus 1 to the n. So this is just the reciprocal. It turns out this number is just 1 over e. Again, if you have a really fancy computer, something like Mathematica, or software that you're using, something like Mathematica, maybe a really fancy graphing calculator, you can see that it turns out that this evaluates to 1 over e. And so the question is this less than 1? Well, e is like 2.6, 2.7, whatever you remember it as. It's some positive number greater than 1. Dividing by 2 point whatever is going to make you less than 1. So yes, that thing is absolutely less than 1. Which means our series absolutely converges. By the ratio test. If you try to do the root test, it would look like the nth root of n factorial of n over n. Now the nth power in that denominator will cancel with the nth root, but you still have the nth root in the numerator. And so asking about the limit as that goes to infinity is way too awkward to try and handle. So that is why we go to the ratio test, because I don't know what to do there. Or maybe royally we. I don't want to just say that. I don't know what to do. Okay. So again, that's a pretty messy problem. Definitely past what I'd expect you to do on the exam or a quiz or something. But maybe WebAssign wants you to do something like that, or Cengage, Okay. So next, let's consider this problem. Now once again, we see a factorial, so that really motivates us to do the ratio test. So the nth term is n to the 100th times 100 to the n, divided by n factorial. The n plus 1 term is n plus 1 to the 100th times 100 to the n plus 1, divided by n plus 1 factorial. So we're doing the limit of the absolute value of those terms, but there's no negatives there, so we don't need the absolute values. N plus 1 to the 100th, 100 to the n plus 1, divided by n plus 1 factorial. divide by a to the n, we're going to keep change flip n factorial over n to the 100th, 100 to the nth. A lot of here. So by design, the factorial pieces are going to cancel, and you're left with n plus 1 in the denominator. That cancels the n factorial piece. You still have the n plus 1 to the 100th, 100 to the n plus 1, n to the 100th, 100 to the n. But notice you have n plus 100s on top and n on bottom. So some of those are going to cancel. In fact, you're just left with 100 of them on top. And in the denominator, all those pieces cancel. So this is n plus 1 to the 100th times n divided by n plus 1. Well, notice this is the same as this. You have 100 of them on top. Divide by one of them. You're going to be left with n plus 1 to the 99th times 100. And can we tell what the limit of this thing is? As n blows up to infinity, you're raising it to the 99th power and multiplying by 100. Regardless, that's getting larger and larger and larger, and then doing things that just make it larger is going to make this blow up to infinity. And so we ask, is this less than 1? No. So it's, and when I say it, I mean that series, diverges by the ratio test. My handwriting's getting worse as this goes on. Test. Okay, so again, both of these examples, you see a factorial, it kind of forces you into using the ratio test. Now, this next problem is a really good example of when we want to use the root test whenever we see some expression just as written to the nth power. Nth powers motivate us to think of the root test, but factorials force us to use the ratio test. So, are there any factorials here? No, so let's go ahead and consider the root test. The nth root of absolute value of tangent inverse of n raised to the nth power. Or I guess the absolute value is supposed to go outside the entire term. But for positive numbers, tangent inverse is already going to be positive. So limit as n goes to infinity, tangent inverse to the nth power, where we take the nth root, this nth power and nth root cancel. So the limit as n goes to infinity of tangent inverse of n. And as n blows up to infinity, tangent inverse, this is a weird problem, is heading to pi over 2, right? I don't know if we remember what the graph of tangent inverse looks like. Am I going to draw this right? Something like this. Yeah, like that. Where this asymptote is at pi over 2. Again, a weird problem, but the question is, do we remember what value we plug in for tangent? That gives us our asymptote that blows up to infinity. That's going to be pi over 2. And again, without a familiarity of trig, that problem just really is awful. But the point is that limit is pi over 2. Do we recall what pi is? About 3.14 ... dividing by 2. The question is that less than 1? Something greater than 2 divided by 2 is going to be greater than 1, right? 3 divided by 2 is 1.5, so something greater than 3 divided by 2 is going to be greater than 1/2. So the point is, no, that does not, the limit does not go to a value less than 1, so it fails So that means the series diverges by the root test. Okay? Now there's one more to consider. Again, this is an nth power, so we want the nth root. Limit as n goes to infinity of the nth root, 1 minus n, 2 plus 3n, all of these to the nth power. And so doing the nth root on the nth power cancels. So this is just the limit as n goes to infinity of 1 minus n over 2 plus 3 to the n. And look at the leading terms there. Limit as n goes to infinity. Now both top and bottom blow up negative infinity or positive infinity. So you can use L'Hopital's rule here. That's going to look like negative 1 over 3. But we're meant to take the absolute value here. So you see a number like negative 1/3, that means, oh, you were meant to slap on the absolute value all the way at the start. So it's going to look like that. And what's that limit as n goes to infinity of the absolute value 1/3? Just 1/3. And we ask, is that less than 1? Yes. So the series converges absolutely by the roots test. And these are the statements that we're meant to make at the end of each of these problems. Say if it converges or diverges, and say what test you used. Now, anytime they use the ratio of the root test, it's telling you about absolute convergence. Recall that the convergences are like kind of tiered, right? Absolute is the strongest, conditional is a little bit weaker, and then diverges is, like the weakest of the three. So if you're happy, you're absolutely convergent, maybe you're conditionally convergent, and lastly, if you're sad, you diverge, right? I say that like there's emotional connotation here. It's kind of not, maybe you don't care if the series diverges or not, but I care. I'm happy, right? I'm happy if it converges. I'm sad if it diverges. Anyway, so the ratio and the root test tell you about absolute convergence, and for a positive series, absolute convergence is the same thing as regular convergence. The only time that absolute and conditional are at odds is if it's an alternating series. So note that this series can have some, or will have some negative terms potentially. And whether you factor the minus sign out, or whether you just take that absolute value and just make everything positive in the end, kind of works out to be the same way. Okay. So hopefully this is helpful. I still don't know how to close this video, so yeah, bye.